Welcome 6th grade math students. This is an assignment that goes with lesson 1.4 and lesson 1.5 from our Math and Focus textbook. Because you're no longer required to know square roots and cube roots, I've given you a supplemental activity. So this cannot be found at the Math and Focus site, but I do have a copy here in front of you, and I'm going to show you a few examples. You should have this with you to be working on, and I'm going to show you kind of how the explication should look. So we have been taking notes on perfect squares and cubes in the classroom. Notice that here it says, I want to show expanded form, and I also want to solve. So I set up the first one for you. It says 11 to the third power. If you remember, that was where we were building cubes, three-dimensional. This little tiny 3 is talking about cubes. And I'm trying to figure out the volume. So when I find volume, I use a length times a width times a height, right? So I'm going to use 3 dimensions, or I'm going to write the base 11 3 times. 11 times 11 times 11. That's exactly what I showed you here. Well, I'll be honest with you, I probably don't know this fact off the top of my head. I do know 11 times 11 is 121, but times 11 again. I did tell students that they could use a calculator if this was getting sticky for them. So calculator, okay, but that does not mean that you don't have to show your work. You still need to show your steps for that. I'm going to take a quick minute and I'm going to try 121 times 11. You are welcome to break out a calculator if you have one. I just don't have one right this moment. So 1 times 1 is 1, 1 times 2 is 2, 1 times 100 is another 100 here. And I need to remember to put a placeholder. Sometimes we say, hi Bob, and the 0 helps me move over to the tens place. Well, 10 times 1 is 10, or 1 in the tens place. 10 times 20, this is a 2 in the tens place, it's actually 200. Or I'll put a 2 here in the hundreds place. And 1 times 1 again is a 1 out front. When I go to add these together, 1 plus Bob is 1, 2 plus 1 is 3, 1 plus 2 is 3, and this 1 plus nothing is a 1. Looks like I get an answer, 1,331. And if you wanted to be really impressive, you could call this, well, if your pen will let you. Hopefully you're working in pencil. I should point out I'm working in pen because I'm on a Promethean. Units, these are units cubed. Do you remember we built these in the classroom with little tiny cubes? That's exactly what we're talking about. How many cubes does it take to make this shape? I would never want you to try this at home. That's why we want to use this exponential form, expand it, and get to a good answer. We can kind of apply those skills we did with the small numbers with these bigger numbers. Number 2. 12 to the third power. Well, that really means I need to take the base and write it how many times? 3 times. And because I'm writing it 3 times, I'm also going to show you multiplication. 12 times 12 times 12. Well, I know for a fact that 12 times 12 is 144, but I don't really know what 144 times 12 is. I'm going to have to figure that out. And again, you're welcome to use a calculator here if you have one handy. I do not, so I think this is as far as I'm going to take you with this problem. I do want to take a look at number 3. Something has changed here. I still have a base. It's all about the base. But this base is different. It's a 6. And the exponent's also smaller. It's not 3 anymore. Well, when it was a 3, I wrote the number 1, 2, 3 times. 1, 2, 3 times. But this time I have an exponent of 2. So that means I can only write the 6 or the base twice with the multiplication. Maybe you remember, oh, this is where we did 2-dimensional squares. And if I'm trying to find the area, I just use a base times a height. Oh, I gotcha. I can only use this number twice with multiplication. Well, 6 times 6 hopefully is a familiar fact. You'll get 36, and we need to make sure we label this. So we don't know if it's feet, miles, or inches, so we're going to be generic. We're going to use units. But units is a straight linear length, and I don't want a straight length. I want to know how many squares are inside. So we call these units squared, or squared units if you were to write it out in word form. Okay? I hope that you are taking a look at number 10 and you're noticing, oh, we're back to an exponent of 3. How many times will I write this? If it's 3D, I need to write it 3 times. And I do expect you to get me to a decent answer. If you take a look at number 5, oh, the exponent's a 2 again. They're mixing things up on me. But I can handle this. If they're talking about just to the second power, I can only write the base twice. And so on. I do want you to show expanded form, and when you're done, solve it. You are allowed to use a calculator for the tough ones. So I understand that 144 times 12, if it's not off the top of your head, you might want to work that out and figure out. Actually, I'm just thinking of this. 144 times 10 would be 144 with a 0 behind it. And 2 times 144 would be 288. So I might not need the calculator as badly as I thought. I think we're going to get 1,728 units cubed. Please double check this at home. Okay. I do want to move down to the next couple sections. I'll give you a hint on just a couple of these in case for some reason it's not making sense and you want to be able to make sure things are going well. So notice something's different here in this next section. My class today was good about pointing this out. They noticed that for numbers 7 through 10, it says write the square for each number. So in this case, they're telling you it's not a mix of write the square or the cube, just write the square. So if I'm going to write the square today of each number, that really means I'm thinking in 2D shapes. Squares are two-dimensional, they're flat, right? So I'm only going to use 2 of these measures, or I'm only going to record the base twice. If you remember, we have the square of 5 in our notes. It was 5 by 5, and it's really 5 on all sides, but I only record it twice for a base and a height because I'm finding the area. Area equals base times height, or length times width. I get to write that 5 2 times. I only need 2 dimensions, and I will multiply to find a good answer. So I'll let you practice that for me in this section. Notice it looks like the bases are changing, but the exponents are all this little tiny 2. They're all squared. That's why it says find the square for each number. Let's look at the next section where it says numbers 13 through 18. Boy, I can't drive this thing. Sorry. Almost there. All right. Here it says write the cube for each number. So let me clear my work from up above. And we're looking for the cube of each number. Well, cubes we know are 3-dimensional. Put on those 3D glasses, right? Like the goggles at the movie theater? All right. So if I'm picturing 9 to the 3rd power, I'm not just picturing a square. I'm picturing a cube. So you don't have to draw this out, but if it helps you to visualize, it's not a bad idea. Well, how long is each side? Well, the base is 9. So the height is 9. And the width is 9. That's 9 all the way around this thing. I can show that with these congruency marks, right? These tick marks going around my geometric shape. Well, be careful. I only want to record this 9 3 times. I'm finding the volume here. It's like length times width times height. This is an L, by the way, trying to make sure it looks like an L, maybe in cursive, not like a 1. So I'm going to use a length, a width, a height. Well, all those numbers are the same. They're each a 9. And I'm going to multiply here to find a final answer. Well, I know 9 times 9 is 81. 81 times 9, well, I actually know that answer off the top of my head because 80 times 9 is 720, and 9 times 1 is 9 more. So I'm going to get 729. Now, if you want to really impress the teacher, hint, hint, wink, wink, you would know that these are units, yes, but these are cubic units. These are those little tiny cubes that fit inside. This is the volume, the inside dimension of a 3D shape. Do notice my bases are changing. The 12, the 8, the 6, the 1, the 2, those big numbers. It's all about the base. That big number, like the biggest instrument in the orchestra. But the thing that's staying the same is this little tiny 3, this exponent. And what is it telling you to do? It's telling you to list the base that many times. Use the base. I'm going to write base really big because it's a big number. It's written as a big font. Use the base 3 times with some multiplication. So 12 times 12 times 12. You might have done that one earlier, but if not, you're welcome to use your multiplication charts to get 144 times 12, and then you're welcome to maybe use a calculator to find me a final answer. So don't stop on me here. Calculators are okay once your work is on the paper, right? So just in quick review, squared. When I have a number squared, or the perfect square of a number, how many times did we list that number? The answer would be twice. When I have a cube of a number, the perfect cube of a number, how many times did I list that base? 3 times. So if you can remember, squares are 2D, cubes are 3D. That also tells you what exponent to look for. That's your exponent that's being used. I can see that my document camera didn't really like my hand interfering. All right, I'm going to ask you to turn to the back side of your assignment, and I'll see if I can get this to zoom in a tiny bit. There we go. Part A. Here the directions say solve. List the perfect squares between 100 and 500 that are even numbers. Well, the perfect squares, we found the perfect square of 100 the other day. Can you look back at your notes for me? What number did we use to find the perfect square of 100? Well, you kind of see that we used 10 times 10. Now those aren't prime, but those are the factors that we used, and we do want a number times itself. That's how we square things. So 10 must be the base. I'm going to show that. We used 10 to the second power, which meant 10 times 10, and it got me 100. Awesome. But I want the perfect squares that are between 100 and 500, so 100 is no good. And I also want to make sure that I'm using the even answers, the even perfect numbers. Well, this is a good start because I'm starting with something I know. Well, could I try the same thing with a little bigger base? What about 11 squared? Well, that would mean 11 times itself, or 11 times 11. What would you get? Check your charts, check your facts, 121. Awesome, I just found a perfect square. Problem is, it's not even, so thanks for playing. We better try again. I'm going to try 12 squared. Well, to do this, I see the base is 12, and I need to record it twice. That's what my exponent of 2 means. And 12 times 12 is actually 144. Hey, odd or even? Look at that last digit. Hopefully you recognize it's even. This is one of my answers. But there are others. So what would make sense a little bigger than 12 to try for my next base? How about 13? Well, that would mean 13 times itself. And if you check your charts or check your facts or stack them up, I think you'll find 169. Odd or even, you might check. Oh, that ends in a 9. That's an odd number. No good. Thanks for playing. Let's try 14 squared. We're getting there. I'm going to try 14 times itself and see what I get. Now, I don't have my charts in front of me, and I don't know if I have this one memorized. So off to the side, I'll just stack them up and see what we get. 4 times 4 is 16. Keep the 6, regroup the 1. 4 times 1 is 4, plus 1 more is 5. We need a 0 or a placeholder to move over to the tens place. 1 times 4 is 4, and 1 times 1 is 1. When I add these together, 196. I couldn't remember that for some reason. 196. Now I must check, is it odd or even? Oh, it's even. I just found another good answer. Now listen, there have to be others. We're trying to get all the way up to 500 without going over. So next I try 15 squared. That means 15 times itself, 15 times 15. And I'm going to let you test that out, but I think if I'm not mistaken, you might get 225. I'm going to put a question mark after that. I'm not sure if that one's really in my head or not. Hey, if it is correct, I know that this is an odd number and it won't be a good result, but I bet I could try 16 squared. I could try the next one to see if it might work. And you might be noticing a pattern here. You're like, 100 is even. How awesome. That's interesting. 121, that was odd. No go. The next one I tried was 144. That was even. That was perfect. A perfect square. And if you take a look at the next one, I got an odd. The next one wasn't even. The next one wasn't odd. The next one, I hope, is an even. There's kind of a pattern happening here, isn't there? So you might not have to test every single one in between if you start to catch that pattern. Now, I do need you to keep on going. I can't remember exactly where it stops. So you might have to get yourself all the way up to, I don't know what, 19 squared, maybe 20 squared. Oh, I know 20 times 20, actually. I'll do this one for you. I know that that's 400. So I'm getting close, and my question is this odd or even? Oh, it's even. I found you another good answer. There might be some others hidden in here. Oh, I'm not quite there yet. 21 squared, and you get to test it out, and then 22 squared, and you get to test it out, and you get to keep on going until you get as close to 500. Okay? You can handle this idea. You're just starting to look for a pattern, and you're double checking after you find the square of the number. Does it fall between 100 and 500, and is it even? Let's look at part B together. Solve. Given that 17, this should say to the second power. It's hard to read that today, so I'm just going to rewrite that. It should say 17 to the second power equals 289. Okay, if we're given this fact, find the square of 170. Well, if this is a true statement, and they're saying it is, 17 squared really means 17 times 17, doesn't it? They say I get the answer of 289. There's nothing to figure out there. But they did something different for the next piece. They say find the square of 170. They don't want you to break out a calculator. They want you to think. Oh, they say 170 squared. There might be a pattern to this. Oh my gosh, I noticed something already. You should be looking at the original one we were given, the 17 for our base. And it grew. This base grew to 170. Well, what times 17 would get me this bigger base? Hopefully you notice there's a 0 at the back. There's kind of a hint of this. You can check your charts. 17 times 10 gets me 170. So what that means is, not only am I going to have 17 squared, I'm also going to have this 10 at the back squared. It's like saying, if I were to break this into factors maybe, that might be a way to think about it. Instead of just 17 times itself, I need to account for this extra 10 that's happening. So 17 times 17 times 10 times 10. Well, if you already know 17 times 17 is given to you, it's 289, and I bet you remember 10 times 10 is 100. You might be able to get me to a really fast answer if you understand the rules of zeros. Or at this point, if you get out your calculator and you want to double check, what would you get with 289 times 100? Notice here they're asking you to look for a pattern. They're asking you to figure out what's happening here. Okay, how's it going to affect my final answer? If the base is growing, well, so is my product or my perfect square. But it's growing, and I'm going to have to think about the factor that I used and using it twice in multiplication. I don't know if I should show you another one of those. I feel like there's one on your test coming up soon. So for that reason, maybe we'll try just for fun. So let me think. What if we said 3 squared? 3 squared we know is the same as 3 times 3, which gets us 9. But what if I said, what's the square of 30? Well, we know 3 times 10 is 30. So instead of just 3 times 3, in a minute, I'm also going to have to account for that extra 10 that's in there, times itself. Oh, if 3 times 3 is 9, and 10 times 10 is 100, I wonder what 9 times 100 would get me. The correct answer here would be 900. So if you test this out in your calculator, 30 times 30, oh yeah, you can find 900 really fast. They're asking you to think about this rule. What are they using to get there? There are a million other combinations, actually an infinite number of other combinations we could try, but hopefully you're starting to see a bit of a pattern there. This last one, part C, solve. List the perfect cubes between 1,000 and 3,000 that are odd numbers. The perfect cubes. I have to be honest, we did not go all the way through perfect cubes in class. We ran out of cubes a long time ago before we hit 1,000. But I want you to notice that there are, well, a couple hints here. Cubes. We're talking 3D, my friends, which means I'm looking for a number that's going to be used 3 times. It's also going to be my exponent, right? Well, I also noticed that the first number they give me, this 1,000, has 3 zeros. Hint, hint, wink, wink. Can you think of a number times itself that will end in 3 zeros? Well, I hope it's looking kind of familiar to you. What about 10 to the third? This would really mean 10 times itself times itself. I list that base 3 times, and 10 times 10 is 100, and 100 times 10 is 1,000. Oh yeah, this checks out. So this is where they got this first perfect cube from. But they want more perfect cubes. They want the perfect cubes that are between 1,000 and 3,000, and we're also looking to make them odd. Well, this isn't odd, and it's also not between. Remember, between leaves up these 2 numbers. It's the bully. So we're going to try the next possibility, which would be 11. 11 to the 3rd power. That really means 11 times 11 times 11. And if you look at the front of your paper, I think we got 1331. I can't promise. I erased my work, so you're going to have to go back and do a double check for me. If this is true, if it's 1331, is this odd? It is, and it would be a good solution. Next, you could try 12 to the 3rd power if you like, which really means 12 times 12 times 12. Breaking out a calculator or looking back at the other side, you can see what we got from this perfect cube. Well, when you check it out, I'm guessing you just found an even answer. It's one that won't work for us. So I'm going to have to keep on going. I'm going to try 13 to the third power next, which really means 13 times 13 times 13, because I'm testing out perfect cubes. And I want you to continue going with this until you get yourself to all the possibilities, all of the perfect cubes that land between 1,000 and 3,000. I think we don't have far to go. You might need some line paper if you're running out of space. Food for thought. I think that this is a very doable problem if you stick with the pattern. Just keep following that pattern. That cube means write it 3 times, multiply it 3 times. I know I had to chop off some of these problems tonight because for some reason my exponents didn't print very pretty. So I'm going to have you look at numbers 9 and number 12. I'm going to rewrite these, and I'm going to take a really close look at this problem before I do that. I believe this says 9 to the third power. So we're going to call this 9 to the third power, and we're going to take away 5 to the second power. And for number 12, I'm going to do a rewrite step for you because I know it's incredibly hard to read. We're going to call this 4 to the second power plus 8 to the third power divided by 2 to the third power. And I give you a hint. We're going to use PEMDAS. We're going to use our exponent rules, yes, but we're also going to use, please excuse my dear Aunt Sally, or order of operations to help you. So let's take a look at this first one. Well, there are no parentheses. Check. But there are exponents. Let's take care of the exponents next. 9 to the third. That means 9 times 9 times 9. And 5 to the second. That means 5 times 5. And notice there's subtraction between these two things. All right, let's try this out. Well, 9 times 9 is 81. Times 9 again is 729. I want to double think this. 9 times 8 is 720. 9 times 1 is 9 more. I think we're good. 5 times 5 is actually 25. So I'm going to solve those exponents first and keep bringing down the subtraction. When I'm done, I'm ready to subtract. I have 729 take away 25. You might want to stack those up and make sure that your ones place is in alignment, and you're going to have a final answer for me. And if you notice, with your great organization, it kind of starts to look like pizza. We've done these before. For this next one, I have 4 to the second plus 8 to the third divided by 2 to the third. Well, I'm going to try my PEMDAS rules. So looking up above here, are there parentheses? Nope. Are there exponents? Absolutely. That was the whole point of this assignment. So I'm going to take care of these exponents next. 4 to the second, what does it mean? 4 times 4. 8 to the third, it means 8 times 8 times 8. I list it 3 times. And 2 to the third means 2 times 2 times 2. It's multiplication in between. Do be careful, there are some symbols that need to come down. So there's some addition here, there's some division here. And you notice when we are doing expanded form, it's like that cheese on your pizza. This step, it kind of gets stretched out, doesn't it? That's why it's called expansion. We're expanding what the expressions mean. Well, let's take each piece of this. 4 times 4 is the same as 16. 8 times 8 is 64 times 8 again. I don't know that right this moment. So off to the side, I'm thinking to myself, 4 times 8 is 32. Piece of 2, regroup 3. 8 times 6 is 48 plus 3 more, 49, 50, 51. Looks like 512 is the cube of 8. How about this one? Be careful. Most popular wrong answer, 6. That's not right. We need to multiply. 2 times 2 is 4. 4 times 2 is 8. Let's bring everything else down. Oh, my exponents are finally done. Took care of those. Bam. Next, I need to look for multiplication or division. Remember, whichever one happens first in the problem gets done first in the problem. And I do not have any multiplication, but I do have division sitting right here. Here's where we'll find out if my cubes and my squares were right. We're going to find out if 512 really divides by 8 nicely. And I hope it does. Does 8 go into 5? Not so much, but it goes into 51 6 times, because 6 times 8 is 48. Let's do a little bit of a subtraction, and I know you might want to see that regroup. So I have 11 take away 8 gets me 3, and 4 take away 4 gets me 0. I'll bring down the next place value. I now have 32 divided by 8. Will it work? Yep, 4 times, because 4 times 8 is 32. When you subtract, there's nothing left. Oh, finally, this 64. That's what I need here. 512 divided by 8 got me 64. I need to bring down everything I have not used yet. I have not used 16. I have not used my addition. And there's one last move, the last thing you could possibly do. Well, addition, subtraction in order from left to right. Let's add these together. Whatever you get for a final answer will go here. Notice we did a pretty good organization. The pizza got a little stretchy right about there, but this still looks like pizza to me. Kind of looks like we've got one of those crazy cheesy crusts or something going on. Okay? I think because we can't read the exponents on the next two problems very easily, I'm not going to create problems for those. We're just going to stop at number 12 so that you get some good practice with us, and you can expect to see these again very soon, kind of spiraling throughout the year.